So I'm pleased to be here and thank all the organizers for the invitation and for the opportunity to come and be here. So the title is Equilibria for Thin-Grained System, Surface Diffusion, and Grained Migration. Though on the way to equilibrium, I'll discuss some dynamics. Okay? So though we've heard various details now, in particular from my colleague Eugene, here again we see some older pictures. Polycrystalline materials, these are solids with many grains. Grain boundaries, those are the interfaces where grains meet. Thin, nano-thin layers, those are from a nanometer to several microns. And typically the grain boundaries migrate to reduce surface free energy. And we heard from Eugene many, many more complicated situations. Okay? But the difference is he's in a material science department, I'm in the math department, so I have to keep to things which are a bit more slow and hopefully yeah, a bit more. So in fact, here we have some classical features of interest. We have here, this is the upper surface. And this is supposedly a thermal groove. There's a, where is this? A grain boundary going through the center there, okay? And one wants to know how this is moving and whether or not there is a grain below. In fact, I have to thank again my colleague Eugene. This is an AFM picture from his laboratory many years ago. And on the right is a picture I have to thank Bill Mullins, okay, who I was pleased to meet at Carnegie Mellon. This is from his 1958 paper, and he was talking about these are different grains and grain boundaries, and they're moving, and he's seeing these waves in the back of the grains, and he's talking about jerky motion. And in fact, an explanation of this, which is very careful and credible, has yet to come through to the best of my knowledge, though the focus has gone on to many other problems of perhaps more technological meaning than these copper films. Okay? And so here again we see once more this 1D nonlinear surface diffusion model of Mullins. This is really the surface diffusion equation in a graph formulation. It's correct, it's just simply 1D. He's the person who gave surface diffusion the name surface diffusion, and it's in this 1957 paper. But then what do you do with a fourth order equation, particularly in 1958? Okay. Maybe it's all you should do, but he linearized it around the planar surface situation. And then this is called the small slope assumption, which is in many circumstances realistic. In fact, some people argue that it's always real, okay, nearly always realistic. But then you want to solve it with some boundary conditions. And what do we have here? Just simply, this is the classical Mullins picture, okay? You start essentially with a flat interface, okay? This is y is equal to, this is height, y is equal to 0. And then this is your grain boundary, exterior surface. And then the thermal groove starts forming to reduce the overall energy of the system, okay? And these are the boundary conditions written down by Mullins to make the problem simple. He made it semi-infinite and had it going out to 0 at infinity. It's symmetric, and his solutions are classical, well studied. So I asked the question, not knowing that on the other side of campus, Eugene and his group was doing something similar. Okay, do there exist other physically meaningful solutions to this problem 2? We also had another motive for looking at this. Okay, and so we want to say physical solutions, at least in a Mullins type context, are solutions that go to 0 at infinity. Even though in polycrystalline systems you don't always really want things going to 0 at infinity, but it's some realistic problem formulation, which is well posed. Okay? And so together with my postdoc, Abiba Kalantarova, just recently, okay, we found a 2-parameter family of solutions to the Mullins linear equation with this far-field condition, okay? And it's again of this self-similar form suggested by Mullins. And this Z has to satisfy U as the self-similar variable. It has to satisfy this 4th-order equation, linear, written down already by Mullins in 1957. But I told Abiba, go find the general solution. So she found the general solution. Okay, these are hypergeometric functions. And then the question is, suppose you want to look only, it's a 4th-order equation, there should be a 4-dimensional set of solutions. But if you impose this far-field condition, that in fact imposes 2 conditions on the behavior of Z at 0, it makes sense, okay? And this gamma, it's the gamma function, so we have these 2 constraints, okay? And then by looking at these equations a little bit, we can see that by fixing any 2 of these Z0, Z prime, Z double prime, Z triple prime, you get a unique solution which goes to 0 at infinity. We were thinking this is probably very well known. Maybe it is. We didn't manage to find it, and we were doing this on the way to looking for something else, okay? If one looks at the equations that we got, if you take this particular, then that's what you get. You get back to a Mullins solution, okay? And then you can previously unknown solutions provided by this description. I haven't checked because I just heard from this from Eugene on the way over, but apparently his solution, I suspect, is in this 2-parameter family, okay? But here's another thing we thought to do with this, because I was thinking we got these 2-parameter family of solutions. What can you do with them other than maybe publish it in engineering? Okay. Maybe it's good for somebody, so we should publish it. Okay. But here, suppose the boundary conditions are all set at 0. Okay. And I was looking, what can we say with this which is perhaps of some use to somebody? So we set the condition at 1, where 1 we're really taking as an arbitrary value along the axis. We say, suppose at 1 the profile has 0 height. Okay? And then suppose we dictate the derivative there as being 1. Okay? That, though this is arbitrary because it's scalable. That yields a solution that decays at infinity and satisfies, okay, that y at this t to the 1/4 space, t in time is equal to 0. So I like to look at this as a decaying surface diffusion tail. So it's a tail moving and decaying, and that also, so why should anybody be interested in one of these decaying surface diffusion tails? Maybe no reason at all, okay? But instead of having to look at the groove, if one wants to go and measure this coefficient, this Mullins coefficient, okay, at least by my comprehension, one can look at this moving point and measure directly there rather in the bottom of the groove where mechanically it's hard to put the system and do the measurements at the bottom of the groove. Okay? So this allows you to make measurements away from the bottom of the groove, just simply at some point at 0 height, which is moving not too fast. Okay? So the rate of motion should give a way of measuring this Mullins, at least in theory. Probably there's so many other things going on to really make it to a real measurement is not so easy, perhaps. Okay? And then some of the work I'm talking about is with my former student Vadim Derkach. Also recently, okay, we've been looking at the nonlinear surface diffusion equation. Just because we're in mathematics, so being a bit uneasy about linearizing everything, at least the notion is to understand what's being said in the nonlinear variant in order to know that if we throw away the nonlinearity, when can you do that without losing perhaps some features which are being attributed to something else? Perhaps, okay? And so we took the surface diffusion equation, the nonlinear 1D equation, and we put in these arc length variables, okay, S, arc length variable for X and Y and T, and then we looked for self-similar solutions in terms of this S and T. Okay, so this is, instead of U, we have this Xi, and this Xi is S, the arc length variable over B to the T to the 1/4. And having done this, and it's now appeared in this paper, Defect Diffusion Forum Proceedings, okay? Then it turns out that Rabkin, Klinger, and then colleagues, they used it in describing pores. At least they wrote down the equations, but they didn't take it out to this problem formulation which we made. Okay, so this is essentially the nonlinear, full nonlinear but 1D model in these big X, big C variables. Okay? And then these are really the same boundary conditions, the full boundary conditions of Mullins prior to his linearization. And the idea is to know, do there exist self-similar solutions to the fully nonlinear problem? It seems natural in some sense. Mullins knew you could sort of write down an equation for it and get a structure function, if you wish, for the nonlinear, okay? But between writing that down and actually proving the existence of one or more solutions, there is there's what to be done. And Robinson, which did numerics for this, but not out to very long, and I'm pleased, Eugene, again, I showed this, Robinson did this already, but he did it in 1971, and the numerics weren't too accurate then. He did it in some heavy computer, okay? And in fact, Asai and Giga, who I was talking to, got partial results trying to prove existence for a self-similar solution. They, in fact, didn't prove its self-existence. They linearized one of the boundary conditions, okay? So, in fact, we've been making progress in this direction, but in fact, our idea is that by using this formulation, this should allow us to demonstrate the existence of these self-similar 1D fully nonlinear surface diffusion equations, okay? And then for some notion as to why this isn't a void of use effort, okay? We can take this out, and Vadim was running numerics. And this, if for some sense of what you get from the linear problem and what you get from the nonlinear problem, the pictures, these are profiles, okay? What's with this? The linear profiles and the nonlinear profiles look roughly similar until you notice that the scale here is quite different, okay? So the linear are sort of all over the place, down to -8, where, and this is going up to m, goes between 0 and 1, 0 and 2, and this is just between 1 and 2 for some notion of the near wetting limit, okay? So what is, so this is down to 0.8 and here, and on the nonlinear one, nothing goes down much below between -1, and the curves all seem to look roughly the same, okay? And nothing too drastic is happening as one is getting pretty close to 2, which is the complete wetting limit. So
it's -0.8 or -8?
I don't see I don't see your, my pointer is, the scales are correct. Where you look, I see -8, and that's -8, and that really is, okay, that really is -1 point something. So it really is drastically different. So my gross intuition is that maybe people are always throwing out the nonlinear, even though it may be able to explain things, even though it's more work to work with it. Okay? That's it gives activities to mathematicians. In any case, one can also go ahead and look at, this is the thermal grooving problem, and one can look at the depth as a function of this parameter. Okay, and so one can see that this gets much deeper for the linear problem, and for the nonlinear problem, this really looks like it's asymptoting to some finite limit. It's not, okay? And if one looks that this is, okay, this is this depth to width ratio, okay? For the linear, this is going off and up linearly. For the nonlinear, this is asymptoting to something quite reasonable, okay? So maybe this is just some hint that maybe it is something which should be explored more. So the title of my lecture promised the equilibria, okay, steady states. So first we're going to talk about this polycrystalline steady states, these spherically capped hexagonal arrays. And this is some system of, Vadim was running these triangles with 3 grains. Okay, and so the question was, in fact, put to us by Klinger, can you tile the plane with, okay, and there exist all these tilings, and there exist tilings which are completely regular, and there exist tilings of this sort, okay? And then you can, the idea which, when you actually look at polycrystalline material, it's typically not so periodic. So it's not so obvious that periodic is what you want to look for, but it's a way to get some information. So Vadim was running these different numerics, slow numerics, on these triangular systems. And these are thin polycrystalline materials in the back of our mind. So these are triangles which have a finite but small height. Just to give some notion, if it wasn't clear already, as to what the conditions are, we're taking the grain boundaries we have here. We have exterior surfaces, triple junctions, thermal grooves, groove roots, interior triple junctions. We have 1 quadruple junction. We've got corner points, midplanes, and bounding planes, all to be taken care of. It's a bit complicated, but basically messy, but nothing too bad. Okay. And then what boundary conditions and equations are we taking into account? We've got this motion by mean curvature, and by all we've heard about faceting, we know that one should really be doing much more complicated things. But our notion is to at least understand in the nonlinear sense what's contained as much as possible in the simpler, isotropic models in order to not lose something perhaps in going to the fancier anisotropic models. Okay? And along the exterior surface, surface diffusion, and this is just your isotropic surface diffusion. It's not faceted, though the methodology could be taken forward and anisotropy could be included in this effort. Okay? Along the thermal grooves, persistence, balance of mechanical fluxes, continuity of chemical potential, balance of mass flux, and then along this interior triple junction line, we have similar conditions as well as at the corners. Symmetry has to be taken into account, or we dictate that as easy. And then all these other things which are obviously important, we're neglecting just for the sake of understanding the equations a bit better, as to having a firm standing on the easy problems, quote unquote. And here you already have seen this, so I flip by this. Okay? Yeah? At the thermal groove, this is where a grain boundary joins up with exterior surfaces. This is just a 2D cross-section, but it's actually a 3D model. Okay? And this is the balance of mechanical forces. It gives an angle condition. It dictates the angle at the triple junction. Okay, and this is this dihedral angle, and it's dictated by this balance of surface free energy of the grain boundary to surface free energy of the exterior surface. And then when you get down to looking at the quadruple junction, where all the grain boundaries, all the grooves meet, then one has to see what's going to happen at this point here where the grooves come together. And basically, if one wants to think what should be happening there, one way to do that is to think that if everything is smooth, then one should have the limiting regularity at the triple junction as if the triple junction lines were coming in in the limit as straight. Okay? In the limit. They could come in cusp, but we're looking at coming in straight. And you get these different tangents to the quadruple junction, okay, at the quadruple junction. The tangents are along the different triple junction lines. What should happen at this quadruple junction? One can ask, we heard about what happens with grain boundaries, and we know that there's this m goes between 0 and 2 because there's complete wetting when m is equal to 2. So what happens at the quadruple junction? Basically doing something rather naive, doing a tetrahedral construction, which essentially goes back to the Cyril Smith in 1948. One can see what the angles have to be and how they have to match together. Rather naive. Okay, you can also do this in fancier contexts. And then you get that there really is this condition to have a quadruple junction. Okay, then you really have to have that m goes between 0 and the square root of 3. It can't get up to 2 at all. Okay? Boris Straumel had something somewhat similar in a different context. So here are our hexagonal pilings with spherical caps. And in some sense, this is motivated by looking back at this classical paper, yeah, of David Horowitz and Safran. They were looking at what kind of different steady-state configurations can you really get. And so they were drawing hexagons. And there's a drawing of one hexagon. Okay, but the question is, if you want to really see what are the equations, what does it come down to, then previously we saw that you could tile the whole plane with hexagons which weren't all the same size, okay? But if you want to get a steady state, then in fact it turns out that they have to be the same size, and they have to have these spherical caps on top, okay? So these are all spherically capped hexagons. So we have a tiling of spherically capped hexagons, and then the natural questions to ask: is it better to be spherically capped, or is it better to be flat, or is it better for the whole thing to break up? One can say about the energy of all these things. And so it's really trigonometry in some sense to prove that it has to all be the same size. But it's a bit detailed. But then if you want another proof other than trigonometry, one can ask Robert Finn, okay, and capillary surfaces. So this, if you like, okay, and I'm also working with John McCohen, who's a former student of Robert Finn from years ago. Okay, so this is, if you wish, where a connection can be made in an obvious sense between solid state wetting and dewetting and liquid, okay, states, solid wetting and dewetting, okay? And so here, these are some details of these spherical caps, okay? And this is some details of the maximum minimal height. And when you look at the details of this construction, just as we looked at the details of the Searle-Smith construction, okay, it turns out that there's this constraint that we got before reappears. You can only have these spherical capped equilibria if m is between 0 and the square root of 3. Okay, so the square root of 3 comes up again, if you wish, as a quadruple junction wetting criteria, and that this is it's a non-existence, shows that this restriction is sharp. Okay, this is from capillary theory. Suppose you have a domain with an interior corner, so you can think of the interior corner in one of the sub-corners of the triangle. We have these triangles, okay? So think about this angle here, okay? And then so for us, that's an interior angle. And then theta is this dihedral angle. So what does one get out of this result from Finn? That there's this constraint that alpha plus theta, if it's less than pi, then there exists no constant mean curvature surfaces over omega which are bounded from below. Okay, and this is by comparison theorems and nothing too fancy, but it's a lot of work in this. It's in this book on capillary surfaces of Finn. Okay, and so what does that mean for us? Because this is okay, that's 2 pi. Okay, that's 2 pi over 3, and this is our dihedral angle, again dictated by Rm. So it turns out that what does this mean? That this alpha plus theta is less than m. There exists no solutions bounded from below. That gives that m has to not be bigger than the square root of 3. And what does that mean? It actually, in fact, means that if m is greater than 3 and there is some solution existing, then it's necessarily not bounded from below. And not bounded from below, that really means that, that at the vertex, which is here, it really has to go through the surface, which is wetting, in other words. Okay, so it's some translation of capillary surface problems to the context of solid state wetting and dewetting. One then wants to know what can you say about these, so you think if you don't want the bottoms to go through the system, otherwise you don't get these spherical caps because they're already going through the system. So there's some minimum for a given size triangle, meaning the given size side of the triangle. Where's this? That's this LC3C1, okay? Then the thickness of the film can't be too small, otherwise there won't be any of these configurations, okay? And then one can see by doing some calculations, which are basically simply technical, one gets that the height has to be greater than what we call this equivalent thickness. That's the height that the system would be if you take these capped surfaces and flatten them out. Okay, so there has to be a finite amount of this material, and we can say exactly how finite this has to be, how much it has to be. If m is 0.3, then okay, LZ, that can be pretty thin. Okay, 0.03 of the side. So given the grain side to the thin, that's a small percent. So that you can get these for thin films. And then you want to ask at the switching, are they energetically preferable? So we compare these capped hexagons to a flat surface. And this is a plot done by Vadim based on the formulas previous. Okay, that in fact the capped is less energy than the flat. Okay, and then one can also say you look at it as a different. You want to fix the volume of a given grain, and then you say, suppose you've got grains with a certain volume. What's the best configuration in terms of capped hexagons for these grains of a fixed volume? Okay, and then it turns out that there actually is some best size of triangle if one has dictates the volume of the grain, which perhaps has some experimental implications. Given you know roughly what the size of the grains are, what roughly should their dimensions be? Then you say, does the system really want to get stuck at this particular size? You know offhand, you dictate the volume, it dictates the size, okay? But basically, you know coarsening should occur by some general intuition. And then one finds that indeed, if you look at this, where is this going back? Okay. Looking at the weighted energy per unit area, then in fact you do want to coarsen. That's not exactly saying the whole thing is going to coarsen very easily. And as we heard from Eugene, the pathway to coarsening can be very complicated, and it's not obvious how you get there. Just so you believe this a little bit, these are Vadim's slow calculations. But in fact, okay, so the initial conditions are these triangles. Okay, that's a flat, thin layer of equilateral triangle. And just a little bit after starts, okay, this is a bit past the initial conditions. And this is the initial curvature. You wait, and in some finite time, the mean curvature goes to being constant. So it really is going to this capped hexagonal state. And you really can see here, this is the profile on the top. This has gotten to be, you can see the capped hexagons here. Here, suppose Vadim was thinking, suppose you make one of the triangles smaller than the other ones. Then if you make it a little bit smaller, but not a lot smaller than the other ones, the system seems to drive back towards the equilateral, equal size grain systems. Okay? But if one continues on and makes the smaller grain too small, it seems that it doesn't go back. And then it's going more and more off into some corner. And then because this is a sharp interface description of the evolution, it can't go beyond what happens when one of the grains disappears, as the program is written at the moment. In the last 5 minutes, 7 minutes, 6 minutes, okay.
No negotiation.
What?
No negotiation.
Alex Soron is good at, negotiating. Okay, then there you are. Okay. So here we have another configuration. Again, in some sense, looking at this paper of Sorolis and Safran, really seeing what configurations are there that one can define and test and say something about, even though they're rather naive. So we have two grains within a finite radius cylinder, with one grain embedded in the others. And we want to know, it's 3D now, and we want to know what steady states exist for such a system. This is joint with Vadim and with John McQuinn. So what are we doing? We're trying to look at the height of, Z is the height of the grain from the midplane, and then this is across, and the other axis is the radius. The system has been scaled so that R is equal to 1 is the outer boundary of the bounding cylinder. Okay? And then it turns out, with a little thought and a bit of work, that if you want two grains to coexist in this system, then basically you have to have a spherical section, a catenoid. This has to have zero mean curvature, and this other part, which is called a nodoid. What is this A and sigma? A is the width from the axis of symmetry out to the neck where the catenoid meets the midplane. And what is this sigma? Sigma is the length of the catenoid from the midplane to the triple junction. So it's half the total length of the catenoid. So we're looking here for fixed m between 0 and 2, m equals 0 trivial, m being 2 being this total wedding. And then we've reformulated in terms of this beta, which is written here. That's 2 pi minus the dihedral angle divided by 2. And we find that there's a 2-parameter family of equilibria for a finite cylinder of radius 1. They're made up of this sphere, which has this radius r0, and it has to meet the axis at a right angle. And it also has this catenoid, and if the catenoid gets down to 0 height, then it gets replaced by a portion of a plane. This portion of the plane, that means that the sphere has detached from the outer ring of the nodoid. And this is your classical equation for a catenoid. Both the plane and the catenoid have this 0 mean curvature. The outer portion is this nodoid, which has, with mean curvature 1 over r0, that's the same as the sphere, so that they meet with the same mean curvature. And the description of a nodoid, you look along the median, and this is some equation. It's a Delaney surface. The inclination angle, that's this phi. So it has some formula, and the way this has been set up has already been done so that these will fit as many of these persistence and continuity of chemical potential and angle conditions that we want to place on the system. when you put all the conditions together, then one gets this algebraic equation, okay, which can be rewritten as a cubic equation for this A with coefficients which depend on sigma and beta. Out of all this, with some considerations, one can come up with a theorem for any beta between pi over 2 and pi. That gives you the whole range from flat up to vertical. There's a smooth function. A is a function of sigma defined for all these sigma between these two limits determined by this, with endpoints, one over the square root of 2 and the other endpoint being sine beta, and the graphs of all these for given for all the set of possible beta foliate this region. And if you don't see what that region is, then we see it in figure 7, which is the next and once before the end slide. Okay? Those are all the steady states you can get. So there's this foliation of this parameter domain of possible steady states. Every line corresponds to a different beta. With all them, they're all coming out of this corner here. That corner is when the two grains detach. Okay? And the other limit on this outer boundary, that's when the triple junction is coming up and meeting the outer bounding cylinder. This is the last slide, but the natural question to ask here is, what can you say about the relative energies of all these different configurations? What's a bit strange, what you can see at least from the numerics, is that if you're down here, with that small m, then in fact the energetically preferred state is the one out here. Okay? One goes way up to the other end, then it turns out that the energetically preferred state is the one up there. Of interest, at least from my point of view, is that if you look at, if one is here, okay, then it turns out that in fact there are intermediate values of m which are not unrealistic values of m. They correspond to a contact angle of 45 degrees or a bit less, okay? And there you have minimum which are in fact not not on this end and not at the other end, okay? So these are physically non-trivial states. You can perhaps guess that's something that would happen because the lines are particularly non-straight. So there's essentially some transition, at least in terms of energy, along some internal line which hasn't been drawn there at the moment. Okay? My notion being that if you at least know what steady states exist, this can give some intuition. Okay? Thank you for your attention.
So in the case where you have the junction coming down and propagate, keep propagating down as you showed, and it hits the substrate, like Eugene was talking about, is there a barrier for it to grow, the hole to grow, or is there no barrier for the hole to grow?
I'm not exactly sure.
Excuse me.
I can't answer that question because I don't quite understand for which of the questions you're referring, which of the particular contexts.
For the hexagonal grains, you showed the hexagonal grains. You showed the quadrijunction.
But if you want to know the answer, you can look at page 96 in the book of Finn. Okay, it's your. I think that there you can see that you have this layer going up the side. It's got a finite cusp, and then at some particular conditions, all of a sudden it's really shooting up through there. Whether what exactly that means, it looks like, so it's shot through and gone off to minus infinity. I'm happy to go past minus infinity, but one has to think how to do that appropriately. Is that okay? That's
Okay, maybe I'll ask you to show me that chapter. Page 90, whatever you said.
96, I think. If I've got the book downloaded, but I have trouble with my external disk, so I can't show it to you, but I can find it. It's a classical picture in this book there, but it doesn't mean if you have to, but anytime you go through a singularity, you want to think what you're defining afterwards, okay? That's why it's in what context. If you want to look at it in a slightly different context, okay? If we look at it here, okay, if one looks at the situation where, in fact, this, if you wish, this triple junction has gone down and gotten to height 0, then, in fact, that's why I'm a bit more optimistic in some sense. It's gone through there, right? But then what are you really getting? You're getting, this is even written here, okay? You're getting a portion of a plane. Okay? So that's really meaning you get a sphere sitting in the middle and a nodal toroidal, quote-unquote, toroidal surface around. Okay? So that's why I can answer the question in different contexts. Okay? So that doesn't mean what's the right context, but there are numerous contexts. Okay.
In the self-similar solution of linear surface diffusion equation or nonlinear surface diffusion, you rescale the x coordinate, right, over bt.
Yeah, that's okay.
Self-similar solution.
It's not written there, but you can show the equivalence of the two formulations.
Right.
There, you can.
Let's say linear. In the linear.
Yeah, in the linear. Yeah, okay.
So we scale x. bt is 1 to the 1/4 power or something.
Yeah.
Should this slope at the origin also be rescaled?
But
Next page.
if you want to find out what your this boundary, I put this at 1 because you can. I'm looking at this set of solutions. What are all possible set of solutions? And then you get, even if you have 3 conditions, you have a 1-parameter family of solutions, so that you can scale that back in there.
Yeah, I mean, in the comparison, this slope may not be 1, may be very small slope. Then the difference between the two solutions may not be that big.
I have lots of pictures, but here the M is out here. Okay, the M. Watch, it's the M. Look at equation 5. M has scaled out of there. Okay. No, that's okay. M has gotten scaled out. So if you take the derivative, okay, with respect to x, okay, and then you take, then that gets rid of this, the bt factors, okay, and then you put that at 0, okay, the slope at 0 is 1, that's really giving you back the slope that Mullins wanted, that's written here. Okay, that really is. There was a typo. I fixed it. That's clean. Okay, that's okay. But thank you, because okay.
Okay, so that's
Okay, thank you.